Good morning. So what I'm talking about, I'm working with Matt Faust and Stephen Shipman, who are in the audience. They'll be here the whole week. I'm here just at the beginning. I'm going to introduce you to some topics that come from mathematical physics or analysis that happen to have an interesting algebraic aspect, hence the title. So this begins with a physical model called the tight binding model. And we start with the discrete version of a crystal, which is provided by a periodic graph, which has a set of vertices, a set of edges, and a free co-compact action of z to the d. So that's what makes it periodic. Co-compact means there's finely many orbits of anything. And here's two examples. And it will be useful later on. I mean, it's similar to this. We choose a fundamental domain of the action on the vertices. And now, the tight binding model involves certain parameters, which are ZD invariant functions. So one is called a potential. It's a map from the vertices to R, think of potential energy. And the other is an edge interaction weight. These are also maybe differences in potential energies from the edges to R. Now, given those data, there's a Schrodinger operator, H, and it acts on, well, it acts on functions, but people are interested in restricting to L2 functions. These are square summable functions in B, but it acts on any functions in B. As algebraists, you don't care about analysis. And well, it's true. I mean, this formula works in any set of functions because you have finite many edges. So the value. So if you take a function, its value at a vertex is, well, you multiply by the potential at that vertex, and then you subtract the adjacent vertices with a weight. And the minus sign doesn't really matter because we're algebraists. It can be any plus or minus, but that's what people write. Now this is self-adjoint. There's a natural, because you have a basis of the just the functions at v, the delta functions. This is self-adjoint with respect to that pairing on the L2 space, and its spectrum of this operator on the L2 space. It's a subset of the real numbers because it's a self-adjoint operator, and this corresponds to possible energy levels of electron in the crystal in this model. And they are in this situation they are intervals in R. And they correspond to ideas like energy bands, and there are gaps between them called energy gaps. And they're edges of the bands. These are some features that people care about. But the topology of R is rather simple. And there's more structure embedded in this because of the periodic, because of the periodic structure. And if you look at it with the right pair of glasses, you see a lot more. So I'm going to let T be the unit complex numbers, the compact torus. And every D tuple of elements of T give me a unitary character for z to the d, or namely for z to z, where the point z comma alpha goes to z to the alpha. Now, picking such a point, I'm going to talk about function c sub z on the vertices. So it's just a function. It's said to be z quasi-periodic if for all vertices and every element of the action, the integers to the d, if you translate the function by alpha, you simply pay the price of multiplying by z to the alpha. And now such a function depends only on its restriction to a fundamental domain of the action, because you can extend it via this equation. And the Schrodinger operator acts on these functions because these are just functions on the vertices. And the formula is a little bit simpler. Because it only depends upon elements in the fundamental domain, I'm going to write it just in terms of them. And so it's the same operator as before. You multiply by its value at a vertex, you multiply by the potential, and then you subtract all the adjacent. You subtract the value at the end of edges, multiplied by the weight of the edge. But if you leave the fundamental domain, you can come back to it with paying the price z to the alpha. And there's a theorem called I call it the Floquet theorem. Actually, I know that's not what it's called. Or is it? Or what's the name? Stephen will tell us what. So Stephen, is there a connection to the real world in our group? So he knows what physicists think. Okay, and so I'm calling this the Floquet theorem. I don't know what it's called, but it says that the spectrum, you get the spectrum. So these are just these quasi-periodic functions. It depends upon the point z, and the spectrum is a set of real numbers. So there's some z and some quasi-periodic function, which is an eigenfunction for this. So you collect up all possible eigenvalues, all possible z's, and you get this. Now you can also apply Fourier transform to L2 on the vertices, and you get this a little more directly because Fourier transform is just a change of basis, if you think about it in the right way. Okay, so now let me go back. I'm going to restate the Floquet theorem. Now, but Z was fixed. We can let Z vary. And then we get and we can think of C as a function from T to the D across the vertices to the complex numbers. We'll call that quasi-periodic if it satisfies the same property that when you translate it. So there's a Z variable there I'm absorbing, in there, but it satisfies the same property. And then you can talk about the Schrodinger operator on those functions. And the point to realize is whatever those functions are. So if you do Fourier transform, they're L2 functions on the torus across V. They're quasi-periodic. If you do algebra, they're actually just Laurent polynomials or matrices of them. But however it acts as a square matrix of Laurent polynomials. So whatever analysis disappears now, and we just have some algebra. We have a matrix of Laurent polynomials, which has some interesting structure. And well, back before we're looking at, for particular Z, an eigenfunction, and that's packaged together now as something larger, and the support of those is of the set is determined by the zeros of this dispersion polynomial. This is simply it's the characteristic polynomial of this matrix of polynomials, and that defines an algebraic hypersurface. Right, this is a polynomial in this space T to the D cross R, and that's called the real Bloch variety. And since people are algebraists in here, this is not Spencer Bloch. This is someone with a Nobel Prize, okay, who's probably also in the National Academy of Sciences, just doesn't do algebraic cycles. And by the Floquet theorem, the spectrum is just the projection of the Bloch variety R. And you can see, these intervals then become algebraic hypersurfaces. So in all these pictures, they're when D is 2, so I can draw them, and I've unfurled the torus. But this is really donut. This is over the donut. And you can see right now, these sheets are perfect Morse functions, which is kind of beautiful, right? Right, 4 critical points in each, Betty number of the torus. You know that, right? Right, Hal? Remember that? Graduate school? Okay, yeah, and so this is because of this I was able to state confidently that these are intervals, although there are other theorems that tell you they are. So let's do an example. So I think the simplest example. It's the hexagonal lattice. This underlies the structure of the molecule graphene, and here's a labeling. So that's the lattices on the left. The middle is just a labeling of the edges in the neighborhood of a fundamental domain. And I'm going to use the same name for the vertices as for the potential, because those are just parameters. And I don't want to mess up the slide. And here's a picture of a Bloch variety there. Now, depending about how technical you are, this may or may not be a perfect Morse function, because these critical points are at on the top and the bottom, like the maximum on the bottom and the minimum on the top are at the same level. But let's not quibble. And this is the matrix we get. It's a fairly simple matrix. Because this graph is bipartite, so all the interesting action happens off the diagonal. And notice that if you take its transpose, it's the same as substituting Z inverse. So it has an interesting symmetry. And the dispersion polynomial is just it's the characteristic polynomial of this graph. It's this function here. It's this simple polynomial. And I mean, and actually looking at this, you can understand very well the structure of this dispersion relation. Or I'm sorry, this Bloch variety is also called the dispersion relation. I mean, there's a lot of different terms for this, like there is in any time physicists get involved with stuff. But, think about all the different terminology we have for things in calculus. Sorry. Anyways, so let me inject some reality into this. So now by periodicity the first equation there about the edge weights is from periodicity, and the second one is because they're undirected edges. I pull on you the same way as you pull on me, or push. And so because of that, it turns out that all these matrices satisfy that same relation as the previous one, that they're transposed evaluated Z, its transpose is that it's Z inverse. And so now if Z takes values in the torus, this compact torus, then the matrix is Hermitian, because Z bar is Z inverse on the torus. That's the defining feature of the torus. And so it follows that that at a particular Z, you have matrix many real eigenvalues, and the block counted with multiplicity, and the block variety is a size of the fundamental domain sheeted cover of T to the D. And so because of that, so here's a picture example where W is 4, and because these are you can always order real numbers. People talk about each of these sheets as a band function, although in this case the variety is irreducible, so they don't really have a, if we algebraic geometers think about it, we don't think about these as separate there, because any piece of one determines all the rest. And there's okay. I won't wax it too much, but this is an example that will come up. In fact, it came up in one of the readings. So this picture came from one of the readings, and the example came from one of the other readings we assigned the people in our group, which hopefully you've all read. So that way I know the people looking at the phones are the people who are in our group, because they've all read all this stuff. And the rest of you, okay. Now, I mean, I'm an algebraic geometer, and what's this worrying about the torus and stuff? You naturally just complexify, and you'll allow the parameters Z and lambda to be in the complex torus. That's the complexification of the compact torus, and of course C is the complexification of R. I guess Bernd read everything too. So now by this relation up there.
It says block variety. Its header is block variety.
Okay, that's okay. Well, okay. How big is D typically, Stephen? Yeah, what is?
I mean, to be of interest to you.
Yeah. Yeah, little d, 2 or 3. From the physical world. There's also an issue that when D is bigger than or equal to 4, because these are determinal varieties, they have lots of singularities, like positive dimensional piece of singularities. And but people look at this case when D is 1. In that case, then the block variety is a curve. And there's this really interesting paper by Mumford in which he studies these directed graphs when D is 1, and relates this to the moduli space of curves. So serious people, not just me, have worked on this. Anyways, but by this fundamental symmetry, the zero set of the dispersion polynomial, it's invariant under a non-standard complex structure, where the pair Z on C star to the D, comma lambda, goes to Z bar inverse, comma lambda bar. That's a complex. It's an anti-holomorphic involution, also known as a complex structure, or a real structure on a complex variety. And so the real block variety is actually the set of real points of a complex block variety. We have an instance of non-standard reality. And this alternate reality, I think, is an interesting feature of the subject, in that it provides a very natural set of examples that are real algebraic varieties, but not with your grandmother's notion of reality. And there's an interesting feature, a little hard to see because of just the way the computer display, because of that, not my laptop. But there's a symmetry here because these are related. There's like a square root involved. That's why there's a symmetry about some central line. But the maximum of the second sheet consists of 3 straight lines on the torus. 2 of them are coordinate subtori, one going in this direction, one going in that direction, and one of them is going obliquely. That's kind of interesting that this edge of the spectral band has these curves on it. These are features that people should find interesting. Do you find them interesting? Do you think about this when you study this in your paper? Yeah, but okay. So I just want to point out that there's interesting features on these varieties, and this. this here is to indicate there's this lives in one parameter family, and when you shrink the parameter, you get two ordinary double points along each of these lines. Yes.
So in the grandmother's reality, they would meet in codimension 2, these sheets. This woman has real codimension.
Yes.
Is this true in the alternate reality?
Sometimes they do. I just, the pictures I have don't have them with self intersections, but they, I mean, they're hypersurface. So yes. So these will typically intersect in a line in a curve. And
well, I expect them to be in codimension 2, right? Because the real isometric matrices.
they're hypersurfaces.
Yes.
A hypersurface.
Needs another sheet, usually in that codimension 1, but in the grandmother's reality.
Okay. Well, I have pictures where it doesn't happen. But that actually no, that case it's reducible. There's an example at the very end that I don't understand because I just never took the time to explore it. It's one of the things people might do later. Okay. Yeah, I mean, this has to do with the discriminant of Hermitian matrices. Yeah. So some of the objects that people care about are very algebraic. So for the hexagonal lattice, if you have equal potentials, I mean, in the hexagonal lattice, you had a matrix which had two diagonal entries. If they're equal, you might as well set them equal to 0, and then two off diagonal entries of which look like some polynomial in the two variables, and the polynomial the inverse of the same polynomial the inverse of the two variables. So if that determinant vanishes, you basically have two algebraic curves that intersect, and it turns out they have 2 points of intersection, and you get lambda squared is the product of these two. These are local coordinates. So you get ordinary double points here. You always get two ordinary double points, always, unless it's more degenerate, in this case of the hexagonal lattice, which is interesting because people somehow believe you need to have a Z mod 3Z symmetry to get these, what are called Dirac points. I was presenting this at my department, and one of the older faculty members started screaming at me that I was wrong. But he's okay. Once I explained to him the algebra, he said, "Oh, wow, I didn't know that." So, I mean, algebra can discover really simple things about really basic stuff. But anyways, there are these two ordinary double points. They're called Dirac points. And these correspond to, so the horizontal, the variables T2 are called quasi-momentum because they have to do with their crystal momentum. They have to do with the wave function in different directions. And so so at this particular energy level, there's some very interesting transport around those quasi-momenta, which is just the way it's a double point, or so I'm told. I mean, I'm an algebraist. So now the thing that I really like, and this is one of the things that I learned from an undergraduate in my department. He's now a PhD student at Princeton. Is that so? This matrix, this characteristic matrix, is a module endomorphism of this module, this free module, and the kernel sheaf of it is called the block bundle, and it's I mean, they call it the block bundle. It's really a sheaf, but I mean, we're talking to physicists, and it's supported on this block variety, and so those are some interesting objects that come from our world. And also the level set of a block variety. So you pick an energy level and you just slice it horizontally. In this case, you get a curve. They call this the Fermi variety. In dimension 3, it's a surface, and it's called the Fermi surface. That's more common to be heard. And many basic objects in this area end up being algebraic in nature, as are a number of properties that have been studied. So that's I mean, when I learned about this, I got kind of excited because I do real algebra. I can travel. So here's a question. This was okay. Here's a list of some questions. There's something called the density of states, and that's to do with the spatial density of eigenfunctions at a fixed energy lambda. I cribbed that from a paper. It's been studied using free resolutions. That was by this undergraduate I talked about, and you can show that a different version of it you get by integrating a certain differential 1 form on Fermi curves. Natural physical questions ask for irreducibility of the Bloch or Fermi varieties. You'll see some of those in our group. And I mean, some of the earliest work that people had in physics were talking about whether these things are irreducible or not. For one thing, if it's irreducible, you know that knowing a small part of this block surface of block variety determines the rest of it by complex, because they're complex analytic varieties. There's another thing called the spectral edges conjecture. So it states roughly that for general operators on a graph, the points on the block variety above endpoints of the spectral bands are non-degenerate extrema of the function lambda. So that it turns out that many physical properties rely on this assumption. In fact, it's just assumed in physics, but it's largely unknown even for this discrete toy box, discrete periodic operators. That's where I first learned about this. Now, there's interest in the existence and persistence of Dirac points, like the fact that for the hexagonal lattice, if a condition holds, then you'll always have Dirac points, and so there's some sort of obstruction to not be able to miss them that happens there. There's interest in the existence of flat bands. This would be where your block variety there's literally flat somewhere. It's where the polynomial over R factors with a linear factor. And there are inverse problems of identifiability, which are called isospectrality in the literature. So this is you have these parameters, you get block varieties. You can ask, how do your parameters obviously determine the block variety, but how does the block variety determine the parameter? And there's some questions about that, which Matt will be thinking about or telling people about. So this is not so new, using algebraic geometry in spectral theory. There's a rather interesting book written in 1993 by Gieseker. Some of you have heard of him. Knorr also, and Trubowitz, maybe not. They studied the Schrodinger operator. That's where you have all your edge weights are 1. That's the standard discrete graph Laplacian on the grid graph. So the easiest graph is just, in this case, Z2, where you have adjacent. You connect up nearest neighbor on the lattice. But then the action of the free abelian group is through a coordinate subgroup of Z2. So AZ plus BZ is how Z2 acts on this graph. And they want the greatest common divisor to be 1. I think it's probably not hard to extend the results to the more general case. And here's a picture of it when A is 3 and B is 2. Okay. People call this an expansion. And what they did in this book is they studied the density of states. They actually gave a formula for it because they were able to evaluate this integral of this differential form. They also showed that the block and Fermi varieties are irreducible in this case. There's a particular differential form which I'm not going to be able to reproduce for you. There's a map from the block variety. They compactify the block variety in a toric variety, and they map it, and it has a map to P1 where R used to be, and there's even a relative differential that they integrate upon. But it's sort of known that the way I'm going to flash a slide without much knowledge coming about that. They show that they study the smoothness of these. They have to resolve singularities of the toric variety, sort of. And what they did is they used the toric compactification of the block variety and then the Torelli theorem in this density of states. And it's kind of a crude toric compactification here. They first of all try to put it inside of P1 cross P1 cross P1 and start blowing things up. There's a more sophisticated one that comes later. And now there was this work. Their main goal was this density of states, and this was presented in a Bourbaki lecture by Chris Peters in 1992, who was a well-known algebraic geometer. And later work compactified the operator on the toric variety. So there's a way to sort of understand the operator in some sense on the pieces you add at infinity, which is it's a little mysterious what they did, because I don't think, I mean, you can see it in the thesis, but it's hard to understand all that happened. Okay, so that's an old stuff. So let me talk about this integrated density states that Bernd was asking about. So I'm going to write HN for the restriction of my Schrodinger operator to, I take my graph and I divide it by n times z to the d. So I just compactify it in a big torus by wrapping up the ends. And that's a finite graph with a lot of vertices. Now, this graph, this operator has vertex many eigenvalues and eigenvectors. It's semi-simple. And now you can consider the discrete point measure of point masses at the eigenvalues. Oops, every talk needs a typo. Eigenvalues, sorry. So that's, that's a discrete measure, and you want to normalize it to have some mass. I'll take the mass to be the size of the fundamental domain that I start out with. And then you can take the limit as n goes to infinity, and you get a measure which has supported on the spectrum. And it's absolutely continuous with respect to Lebesgue measure, so you can talk about its density. I don't think those words are used, but you see that. And I think this is what I get from reading literature. They call this the integrated density of states. And in the book by GKT, everybody refers to this book by these titles. Like, we know, GKZ, they have GKT. Okay. So the point is, they show there's a differential form on the Fermi variety. These are the level sets. And this differential form they show is a section of the sheaf of relative differentials from the compactified block variety B1, such that this density is this integral. And this is a differential form on a cycle. And this is the sort of thing you can evaluate and get actual numbers. And they do. And as I understand it, obtaining this was the purpose they went through all this other mathematics. Is that right, Matt? Okay, or Jordy, you've read the book a little more carefully than I have. Thanks. Okay. I mean, it's good to not be completely wrong when you're in front of a crowd of people. So now it can happen. So here's another example, which is algebraic in nature. It has to do with spectral edges, and I point out this is an important assumption in physics. So like any delicate thing in physics that appears to be true, it's assumed, and people get on with their lives. And we mathematicians are sort of going behind the parade with shovels and picking things up. That's right. Well, I mean, mere symmetry is that. And it's a pretty wonderful stuff they leave behind. Anyways, so each spectral edge, so here I have a block variety, its projection to the vertical axis gives me bands. In this case, the two lower bands overlap. And you can either think of the actual edges you see, or the image of each sheet as a band. Your pick. So each spectral edge, so the edge of one of those is the image of a critical point of the function lambda, which is the function we're mapping them to on the block variety. And the spectral edges non-degeneracy conjecture posits that generically, for generic data, these critical points are non-degenerate. And that means that it's like a smooth mountaintop versus something highly singular versus non-isolated. And Peter Cushman he believes Dirac points are non-degenerate critical points, so I'll agree with him. He has a reason for this. And so one thing you could do if you wanted to study this is to study critical points, which are somewhat more algebraic. Not just the actual maximum of each band, but the critical points in general. And well, the equations for the critical points are not very hard. You just take, well, you have to be on the block variety, and then if you unwind what it means for lambda to be a critical point, you get these basic torque derivatives. I use torque derivatives because these don't change the Newton polytope. And okay, as I say, all polynomials have to support a subset of the Newton polytope, and I want n to be, well, n is the Newton. Yeah, all polynomials have the same their subsupport is a support of this. So I'm just going to consider the whole Newton polytope of the dispersion polynomial. And just by Cushy-Rekos theorem, because these have all the same support, you know that the number of critical points, the number of solutions to this, is at most the volume of the Newton polytope normalized appropriately. That's a standard input. You can even get that from Wikipedia. When I submitted this to a physics journal, someone didn't like a version of this because they said it differed from when Wikipedia's rendering of Cushy-Rekos theorem. And so I thought it was really funny. They're telling me that I don't know what Cushy-Rekos theorem is. And I learned it from Chovansky in the math department here when I was a postdoc. Oh, I should have said I'm glad to be at the Fields Institute. I was here when it was first moved to Toronto. And I was a postdoc here, and I attended programs in here. And I also got to be here last spring, which was nice. And I spent a sabbatical year here as well. Anyways, so the number of critical points is at most this volume. That's an inequality. Let me tell you a little bit about that. So now let n be the Newton polytope of the dispersion polynomial. Its projective torque variety compactifies the ambient space of a block variety. I'm assuming something about the integer span of the weights, but let's leave it at that. And it turns out the critical point equations are a linear section of it. That's one of the ways of seeing where we get Kushner-Renko's theorem. But it also tells us that, I mean, if you have a linear section of a variety, which is dimension 0, then the number of points counted with multiplicity is the degree of the variety, which is the volume of the Newton polytope. And this tells you when this inequality I talked about may not be sharp. It can fail to be sharp only if there are solutions to the critical point equations on the stuff you added. So this is the ambient space of the torque variety. This is the full torque variety. So this is the stuff you add. I call it the boundary of the torque variety. And that's just a union of orbits that correspond to the faces of the Newton polytope that are not the whole polytope or its base. So that's I mean, this is, in general, we failed to get for sparse polynomials, you fail to have the expected number of solutions when there's solutions at some asymptotic direction, infinity. In this case, they're actually on a physical object on this torque variety. So now, using the okay, and now on each face of the Newton polytope, the corresponding intersection with the orbit you can get by looking at the critical point equations restricted to that face, which are called facial forms, and oh boy, homogeneity, sorry, 2 typos. It's a good talk. On facial forms, it turns out that if F is a vertical face, it's you have linear relations among your equations, exactly as many as the codimension of the face, and that tells you that the critical point equations always have solutions on the closure of the face. So the part of the orbit corresponding to the face together with its closure, which is the Newton polytope, which is the torque variety of that face, in a very natural way. Yeah.
This has nothing to do with this polynomial coming from the determinant of the law.
Not right now.
At this
stage, yeah. Yeah, this is if you have any section of a torque variety. But this part, and this, so the fact that we're not taking derivatives with respect to the lambda direction, the vertical direction, is why we have this homogeneity with these linear relations on the vertical face. But that just has to do with my optimization. The variable I'm optimizing is the vertical variable here, which you could, if you're doing any polynomial optimization, you could arrange that. Now and if it's not vertical, then it's not hard to see the critical point equations have a solution, again, using homogeneity, if and only if the part of the block variety along that face is singular. And so one can conclude that the number of critical points is the volume, if and only if there are no vertical faces and the block variety is smooth at infinity. And in this paper with Matt, we go on to check this in some cases, but I just want to point out that you can talk about the solutions in the wrong place by using some simple, these are terms that are a little more intuitive than no solutions, and we can study them. And now with Faust and Robinson, another A&M undergraduate who's now a graduate student at Michigan, we explained some contribution. We call this a structural contribution. It comes from vertical faces and from certain oblique faces, meaning non-vertical faces, that are determined from the structure of the graph. So by looking at the graph, because it's a graph operator, we can come up with some contribution we call n-struct, and then we're able to show the number of critical points is at most the volume of the Newton polytope minus this contribution from the structural stuff. And what I want to point out here is that this whole story here has led to, at least not this part yet, but the previous part, has led to a very interesting theme in polynomial optimization. So these critical point equations, I have a hypersurface, and then I have some partial derivatives of it. So, and that's a square system. It's highly non-generic because only the first equation you have any ability to play with parameters, and yet in many cases people find that these equations are generic enough that they have the expected number of solutions given by our basic combinatorial bounds. And this this is I did some work with Paul. Sorry, Paul, and other people in this room have seen or have seen instances of this theme in Pauling optimization. But its origin was looking at these particular questions, because this is the first place that we saw an example of this. So when Victoria asked this question about this Hovansky basis also, having leading terms being the toric parameterization, it's another example of a phenomena that people have discovered that may end up being a more interesting theme than you might thought of when you first saw it. It may not be just a curiosity. Certainly this is not a curiosity. And as I will try to argue later this summer, this is something for people who maybe from our community to sink their teeth into. The paper is nearly written. Anyways. Oh, okay. So now I'm supposed to show some pictures. So let me. Yes. Yeah, so here I have a page here. So, oh, where is? Oh, it needs to remember to wake up. Okay. Right. Yeah. So oh, that's okay. So here I have a page. It's actually on my website, but of just some pictures of these block varieties. These are all. This one you already saw in the talk. These you already seen in the talk. These are just different block varieties for different graphs that I put together, and just some examples. So here's an example of one that has 4 Dirac points, only 2. This is a relative of a famous example of Filanov and Kuchkovsky, in which you have a very simple graph which has a non-isolated set of critical points, which is not so. Some other examples, these ones have to do with certain coverings, a way of getting more interesting objects. Here's an example of a flat band. This is the Lieb lattice. It has a flat band. Here I have edge weights 1, and you get this factorization. If you take general edge weights, using the results that I mentioned, you can show that the spectral edges of non-degeneracy conjecture holds for this, simply because there's exactly 12 critical points that don't correspond to the vertical faces, and you need at least 4 in each sheet, and that tells you have a perfect Morse function. Some other weird examples. This one, it's hard to see here, but this Fermi variety consists of 2 pairs of parallel lines that meet, and they go from one sheet to the other with Dirac cones that are somewhat sideways. Here's another random example. I call it this because the first example I generated, where I took random numbers, whereas these other ones, to get this unusual behavior, you had to do a little bit of tuning. But I took random numbers, and this had a Dirac point on it. So that's hence. I'm sorry. It's a little. I should point out that okay, at least on my computer, these are animations. You want to see what they look like? Yes. Oh, there are parameters. So what happens is I can choose a parameter for each vertex and a parameter for each edge weight. And yeah, the operator. Well, I mean, I just typed in some numbers. Yeah, the operator is random in that sense. And I accidentally found one that had this interesting Dirac point. So I decided, I was preparing these slides for a talk once, which was just these slides, and so I didn't play with it further. But here's the K4 graph. So this is a cover of the complete graph in 4 elements. Here's another. I mean, let's see. I wonder if I have any. Actually, maybe we should look at this one. Yeah. Oh, okay. Yeah. So here's a better rendering of that one. It's a PostScript file. You can see the features I was talking about. Okay, I don't want that. Anyways, I just want to show off some pictures. There are lots of. Here's another interesting one. It has this non-isolated set of critical points, and these mean something or maybe concern people in physics. But there's lots of interesting examples here. It's been kind of fun, maybe too fun to play with them. Let's see. Anyways, so that's what I want to say is one of the possible projects for people to do is to pick a graph and play with the parameters and find out to study the features you can get on it, on this real algebraic variety, Dirac points, critical points, etc. There are people have published papers in physics journals where they've studied one graph or a few graphs and showed certain properties of a very small number of graphs The way we generate these was we wrote a computer code and we ran something on a cluster briefly and generated millions of examples. We say literally all graphs with particular properties, many millions of them, and then we try to sort from those some which seem to have some interesting properties. In particular, it got so interesting we had to write a paper on some of the things we discovered before we could write about our software project. But even the fact that because they're algebraic and because there are things called computers, you can study them in large as opposed to one at a time. And also anything you see, you can prove, right, using symbolic computation. My favorite technique is to reduce mod p and prove something, and then try to explain to physicists why this works over R. That's kind of a fun thing to do. It's best not to do it with a skeptical referee. Yeah, so here's another thing. You can. This is the hexagonal lattice, and it had edge weights A, B, and C. And it turns out that there's a discriminant here. We'll call it the block discriminant. It's a very nice polynomial. It defines these three lines and the line over here. And it turns out that when it's positive, but when A, B, and C are positive, and when this is positive, the edges form a non-degenerate triangle. And when they form a non-degenerate triangle, you always have two Dirac points. When they don't form a triangle, there'll be two Dirac points somewhere else in the complex variety, so they don't count in this world. And you get something highly singular when you're on the discriminant. And where this occurs has to do with which one of these factors vanishes. So which one of these? Okay, I should point out, you always get, because of the symmetry and the alternate reality, there's actually three different ways to see this. You're always going to have critical points where z is plus or minus 1. All the coordinates of z are plus or minus 1. People call those the corner points. And since I'm out of time, I just want to show one more example. I call this Robinson's graph because Jonah showed this to me. And it has a very fascinating block variety. It's a very simple graph, very fascinating block variety. It has singularities. I think there's two singular points here, at least. Critical points at infinity, so asymptotic critical points, which I mentioned we can count. And it's kind of a challenge to study this because there's a lack of tools for treating non-standard real structures. If I go ask the software I've written, do real root classification or software other people have written, they'll tell you what happens to the standard real structure. To use the non-standard real structure, you may have to re-embed it so it becomes the standard structure, and then you're going to pay an incredible price in complexity. And there doesn't numerical methods don't care about this, so that's a positive. That's a plus for numerical methods. But studying things symbolically, there's some of a lack of implemented tools. And here are two views of the block variety. I didn't study this very well, but it looks at it as two singular points. And there's also an apparent curve of self-intersection, but I'm not able to tell if that is a curve of self-intersection or not because I didn't really spend time studying it. But maybe y'all can later this week. So, oh wait, let me just, so here's some bibliography, and I'm out of time in 52 seconds.